For this proof, we have a constructive proof. If n is even and n is between 4 and 20, then n can be written as the sum of two prime numbers. So this is an example of a constructive proof where I will directly list out all the even integers between 4 and 20 and show that they can be written as the sum of two prime numbers. As mentioned before, this is an example of what's called the Goldbach conjecture. The Goldbach conjecture is the claim that if n is even and you take out this hypothesis, then n can be written as the sum of two prime numbers no matter what. This is unproven at the time of this recording. At the time of this recording, this has been tested for every even integer up to about 4 times 10 to the 18th. So 4 million trillion, 4 quintillion. And this has been tested that far up, and every single even number that's been tested works like this. Of course, that's not a proof for all even integers because we can't be certain that the next one wouldn't work. Okay, anyway, but for this one, for the sake of practice, we're just going to prove this for all even integers between 4 and 20. Now, this is a constructive proof, so we will directly test every even integer, every even number between 4 and 20. So I'll write 4 equals, 6 equals, 8 equals, 10 equals, 12 equals, 14 equals, 16 equals, 18 equals, 20 equals. And just simply directly test them all and see if we can do this. All right, well, 4 is equal to 2 plus 2. That's the sum of two prime numbers. 3 is equal to 3 plus 3. And that's the sum of two prime numbers. 8 is equal to 5 plus 3. That's 5 and 3 are both prime. 10 is equal to 7 plus 3. That's one way it can be done. And I'll just mention parenthetically that this one can be done a different way. So that's also equal to 5 plus 5. Now I kind of switch colors just for emphasis. The proof only asks us to write it one way. So the stuff in red here is strictly optional. We only have to write it one way as the sum of two prime numbers. But 10 actually could be done a couple of ways. 12 can be written as 7 plus 5. 14 can be written as 11 plus 3. It also could be written as 7 plus 7. So there's a couple ways that could be done. 16 is equal to 13 plus 3. And also could be written as 11 plus 5. 18 can be written as 13 plus 5. Or it could have been written as 11 plus 7. And finally, 20 can be written as 17 plus 3. Another option would be 13 plus 7. So the stuff in red over here is strictly optional, and so I kind of marked that in a new color just to emphasize that it's not required, but could be done if you wish to list out all the ways it could be done. But all that was required was listing it out one way. So the very unoriginal conclusion is that therefore every even integer, every even number between 4 and 20 can be written as the sum of two prime numbers. And that's the end of the proof, and so I'll use some kind of end of proof symbol to denote the end of the proof. So this is an example of a constructive proof where you kind of list out all the possibilities, and there's not a whole lot of creativity in how this is written up. You just kind of test things directly to make sure they work. I wanted to just to conclude this video by showing that this actually does happen in real mathematical proofs every once in a while. So what's on screen right now is something called the Bertrand postulate, which is the claim that for every number x, if you take x and then double x, somewhere between x and 2x is a prime number. Okay, now the proof of this is actually pretty long, as you can kind of see, and pretty hairy. If you kind of see here, there's a lot of stuff here, and this is taken from the textbook Introduction to Number Theory by Hua. what I wanted to point out is that the way the proof goes is that the first part of the proof is showing that it always holds for n greater than or equal to 4,000, and then the end of the proof lists out directly a string of numbers such that one prime number is less than twice the next prime number. So that's a very constructive end of the proof. So sometimes, I just mentioned this parenthetically, obviously that's not on the test, but I wanted to mention parenthetically so that sometimes in real mathematical proofs, being able to do something constructively is important, even though it doesn't require a whole lot of creativity in how it is written up.